So what I'd like to do in this video is review average rates of change. I'm going to be abbreviating this anytime I copy it down to AROC for average rate of change. Now suppose that you have the graph of some function. We'll refer to this as y equals f of x. Suppose also that I provide you two different x values. We'll refer to them as x equals a and x equals b. Then associated with these values of x, there will be a y value, a corresponding point on the graph. Now with these 2 points, we'll call them a comma f of a. F of a just represents what you would get if you were to plug it into the function. And then we'll have b comma f of b for that. Now the idea is that if I were to connect these 2 points with a straight line, that straight line would represent, if I were to keep a constant rate of change, this is the rate of change that would be necessary to get from this point to this point. This line is referred to as a secant line. This is a line connecting two points on a graph. Or you can really extend that to most geometric figures as well, like circles. But we'll save that for later on in the semester. The average rate of change, as it were, is going to be the slope of that secant line. We typically use M to represent slope, and we'll use SEC to represent the Southeastern Conference of College Football, or, secant. Now what I'm going to do is apply our famous old slope formula and do a y2 minus y1 over x2 minus x1 and call this f of b minus f of a all over b minus a. So this represents if I were to go from this point to this point at a constant rate of change, this would be that constant rate of change. Sort of like when I'm driving to Grand Rapids, my average speed was 60 miles an hour, even though I wasn't necessarily doing 60 miles an hour the entire time. Now, another way to envision what's going on is rather than labeling these points as A and B, it will happen on occasion that people will define the distance between these 2 points, this horizontal distance, as simply h. And instead of referring to this guy out here as B, they'll refer to it as A plus h. Now, in the event that we do that, this is going to look a little bit different. This will be f of, instead of b, we'll use a plus h. A will stay the same. And then in your denominator, instead of b, we'll have a plus h. But if we have a plus h minus a, that just represents the distance between them. That would be h. You may recognize this formula from your pre-calculus class. This is known as a difference quotient. Well, why do they call it the difference quotient? I'll tell you, Patrick. They call it the difference quotient because in order, you would subtract the numerator and then divide by h. Fancy name for subtraction is difference, and fancy name for division is quotient. Now this represents an average rate of change. An instantaneous rate of change. Instantaneous rate of change. If I wanted to compare this to the Grand Rapids to Clinton Township problem that I discussed in the last video, your instantaneous rate of change, or your instantaneous speed, would be you glancing slightly down at your speedometer and saying, how fast am I going? That lets you know how fast you're going right now, as opposed to an average rate of change. So for an instantaneous rate of change, we need only 1 point. We're going to refer to that 1 point as A. Now, what we would need is this for a rate of change. We don't use 2 points to define this line, we simply use 1 point. And this line has a special name. It is referred to as a tangent line. So this is the line that intersects the curve without passing through. the curve. Now, the idea behind making a tangent line, well, it's kind of difficult to find the slope of a line if you don't have 2 points on it. So what we do is we start approximating. What we do is we make this second point a variable point, and we allow our first point to be a fixed point. And we take this second point and simply move it closer and closer on the curve to the first point. So the closer a second point gets to the first point, we wind up with something very close to what is the tangent line. So, how do I make a tangent line? Let B get really close. I'm going to throw some extra L's in there. Really close to A. Or if we wanted to go with the secondary definition, we would want the distance between these 2 points to get really, really small. But the distance between the points is defined as h. So we could also say h gets really close to 0. What I'm going to do is in my next video demonstrate what that actually looks like. Be sure to have a calculator handy if you'd like to play along. I recommend a graphing calculator, specifically a TI-83 or TI-84.